Hey guys, my name's Daniel, aka HashLips, and welcome back to the continuation of the Solidity beginner tutorials. Up until this point, we have discussed a lot of concrete concepts in the Solidity programming language space, as well as general coding structures. In this tutorial, I'm going to be talking about structs and what they are. Structs is probably the most interesting data type that you can have. And the reason for that is because it's a custom data type. It's something that you can build up and really customize to your needs. And I'm going to now show you exactly how to do so and use it. Before declaring a struct, you really need to think of a use case for a struct. Now, a struct can be seen as a blueprint of creating an object, and usually when you refer to object-oriented programming, a struct is like a little class, a blueprint of something that it can have attributes, it can have values, it can have different kind of states that you can manipulate and keep track of. It's like a little object. Let's take an NFT for example and see how we can make a struct for it and then give it some attributes that we can save on chain. We can start off by defining a struct by typing in the struct keyword first. Then we have to give it a name. Now this can be like animal, it can be a cat, whatever you want to call it. I'm going to just call it NFT. This is my NFT struct. Now, at this point, for those of you who've seen my previous tutorials, maybe we can even use the struct to define the DNA of our NFT and maybe things like layers or whatever. But let's keep it simple. I'm going to define a name, and in order for me to give a type to name, I have to say this will be of type string, and it's going to be a name. It's going to be able to have a name. In the blueprint, I also want this NFT to have some kind of DNA, which we are going to make of type uint256. So it's going to have DNA. Then the last thing that this NFT would need is maybe something like a rarity. Now we can also add enums and much more complex types in here. We can even add a struct in a struct if we really wanted to. But I think for now, let's keep it to two variables or two fields that this NFT could have. Now, in order to use this struct, much the same as a enum, we can now go and define a type of struct. For example, we can basically now declare a mapping where we say a mapping of address. That won't be the best idea, but let's say a mapping of a uint256 is going to refer to an NFT, okay? And that mapping is going to be the NFT list or NFT map. I'm going to call it mapping. It's not the most creative name, but this is possible, right? We can say that from our previous tutorial on our mappings, instead of it just being a normal address or something, we can actually map this to a struct and actually get these values back. We can also go ahead and create an array of it. So we can say we want an NFT array now, and we're going to make this maybe public, and we're going to call it our NFT list. And that's perfectly fine. So I just want to show you that there's numerous ways of actually creating these structs and saving them. Now, what I would like to do is actually stick with the array. We're not going to show the mapping. Both of them kind of work the same anyway. But I want to show you how we can now instantiate and create these structs and maybe push them on as a list of NFTs that people own, whatever it could be. How you work with a struct and how you kind of get to its values is quite simple. If you have created a struct before, then you can simply refer to its attributes with the dot notation. and I'll show it to you in just a second. So let's start off by creating a function. So type out a function, and in here we're going to say add NFT. Now our add NFT is going to be a function, and it's going to take a parameters, but also going to be public. The two parameters that we wanted to take is basically a name of the NFT and the DNA. So we're going to say we need a string of name, and I'll get to this in a bit later, but we need to add memory when we work with strings. Then I'm also going to say that we need to have a UN256, and this is going to be our DNA, right? Once we have this, we actually set up to immediately start adding to our array. If you can remember, adding to an array is pretty simple. All you have to say is .push. And once we've pushed onto the array, it should automatically be there. But now, what do we push to an NFT type? Well, of course, we need to push an NFT. So let's, above this push line, go and create a NFT for us to push. We can now go and say we need to make a new NFT type. And when you specify this, you still have to specify a storage type. Much like string and structs and mappings, we need to kind of point it to memory or storage. Now, storage is something that's living on the blockchain, and if you're working with variables that's already existing in here, so usually the type that you want here that can just be disposed of afterwards is type memory. So you have to say that we are going to create an NFT type memory, which is going to be our new NFT. And that's all we want to do, right? We can just specify it like this. And then we can simply afterwards go and add each attribute. So because our NFT, this one, because it's of type NFT, will be able to have a name and a DNA, you can say new NFT.name is equal to something. Also, you can say new NFT.DNA is also equal to something, right? And the somethings that we can equal them to is our parameters that's being passed in through our function at the top. Once we've done this, we have this NFT in memory, and we've basically set its name and DNA, I would say, in the long way. This is a very long way of fleshing out your NFT, but I'm going to show this first, and then I'll show a different approach. Then we can push this new NFT onto this array. And why can we do this? Because this is of type NFT arrays. And that's all we need for this program to really work. When we want to actually read properties of an NFT, we can read it with the dot notation like so. So for instance, we can have another function down here to say get NFT name. And all we need to do is maybe in our parameters specify an ID. So I'm going to make a new uint, and I'm going to say, well, we need the ID or the index, and it's going to also be public. And what this is going to do for us, it's going to return a value. So it's going to returns a string. Okay. So you can't return string just like that. I think you have to say string memory, because we're going to return a string. Basically, we just want the name of this NFT, right? Based on what index we give it, sitting in this list, it's going to check its name. We can also return the whole NFT. Maybe we should do that first. So I'm just going to say we're going to return the whole NFT. So all we need to do then is say return the NFT where the index is the index. All right. So if we do that, then we can just return it. And remember, this can be a public view function because we're not changing the storage, the state variables. All right. So now let's go and check this out. Remember, I said this is the long way. I'll show you now a shorter way, but let's go and deploy this contract. Let's go and remove the previous contract. Make sure we're on my struct, deploy it, and let's check it out. Now we've got this NFT list, and if we go and specify, and I see this is called get NFT name, I realized that we do have our NFT list, so we can get the whole NFT of this. So maybe we must just get the name. So let's go and change this to say, perfect, we're going to return only the name. So once we've gotten the NFT over here, right, remember that we can use the dot notation to return only the name. And then we are going to return a string over there. Let's just save and redeploy so that we actually have a few useful functions instead of two of the same function. So basically, if we look in the NFT list and we look at index 0, nothing gets returned because there is nothing in that index. We first have to create an NFT. Let's call this NFT HashLips. And for the DNA, we're just going to give that. I'm going to say transact, and I'm going to make another NFT and call it Teddy. And this one will have different DNA. I'm going to say transact. Now that we've created these two NFTs, we can again check the NFT list. And when we do that, you'll see that we get this data structure back. We get a string and a uint of name and DNA, and there's the values. Similarly, we can go and check number 1, and there's Teddy. Now what we can also check is getting the name of something. So let's say we want get the NFT's name of 0, and then it returns HashLips. Now that's just a very simple example of how you can work with structs and how important structs can actually be. For the last example, I just want to show you a quick way of actually instantiating an NFT. You don't have to add all these things, even though you can. I'm going to comment this out, and I'm going to duplicate this to show you this in a new line so that you don't have to rework this example. Basically, on instantiation, you can equal this to NFT and then open your brackets, and then you can simply pass the parameters such as name and DNA, and that should be more than enough to instantiate your new NFT, and then you can also push it down here, as long as the order of this is the same as how you've structured it over there. And that's basically the struct example. I hope you guys enjoyed it, and let's look at the next concept in Solidity. To talk about my next concept that I want to convey to you guys, it's data locations. What do I mean when I say data locations? Well, any data that we input, save on the blockchain, give to the blockchain, has to be stored in some way. It has to have a location where it lives. It has to have memory that it's sitting somewhere. Now, when we talk about the 3 different storage locations, we're talking about, or data locations, we're talking about storage, memory, and callback. Now, when I talk about storage data, this array here of NFTs, this is considered to be storage, a storage location, right? We store this on the blockchain. This is going to live there forever. So think about storage as something that you put in a storage space and it's living there. This space is yours forever, and you put something in storage. All right? The next data location that a variable can live is memory. And now you see where I've specified memory before. Memory is specified sometimes just after defining a data type such as a struct, which we've declared here, an array, or strings. The reason for that is because these data structures need to live somewhere, and we need to kind of explicitly explain to the blockchain or the Solidity compiler so it can work with the blockchain, is how do we want to store that data. If you look at this example of add NFT, we're basically creating a new NFT from a struct over here, from the structure. But this NFT does not exist on the blockchain yet. It's simply in memory. We do, however, on this line, put it on the blockchain by pushing it to the storage variable over here. So think about that for a second. We're only using a memory variable here to create, and then we push the real one onto storage. You'll sometimes see that strings require you to put in memory in front of it here before we pass through a parameter. That is necessary for these type of data structures because uint 256 doesn't need it. I think it's because it's a primitive type. It already knows how to handle that. And for strings and more complex types such as NFTs, structs, or any struct and arrays, we have to kind of explicitly say where that data needs to be stored for the time being, or are we working with the actual storage variable? Let's take a look at an example. I'm going to put a function here called update NFT, make it public, and open the braces. Then inside here, I want to be able to update one of my NFTs in the NFT list. This will be an example where we explicitly tell the blockchain that we are working with the variable that's already on the blockchain and simply modifying it. We are not creating a new structure and pushing it because that's already what we're doing here. We are simply going to work with the storage variable. How do we do that? Well, we can say NFT, which we declare the struct at the top, and then we can specify that this is of type storage. Now when we work with this, we can say this is our NFT to be updated, like so, right? Now, when we do this, we can simply say that this NFT to be updated should be equal to something. Now, what do we equal it to? Well, we can say we want it to be equal to the NFT list, and let's pass a parameter ID. So we can pass in a uint 256 and call this ID, and then we're going to pass this ID over here onto the array because we want to get the index, right? So actually this is the index, so let's change that to index as well. And basically by doing this, we've literally grabbed one NFT. If you think about it, we've grabbed one NFT of this list. We said we are pointing to this NFT on storage, and whenever we update this one, it will update directly the one in this list on the blockchain. So for example, if we now say NFT.name should now be something that we've updated it to. So maybe a good example will be to provide a index and a string, which will be type of memory because we just want to use this string for the time being of this function. And let's call it name, right? We're going to update it. We're going to set it to the new name. And that's it. Once we've done this, we literally, we just have to do it on the right NFT, on this one. Once we've done this, this has actually updated the blockchain. We didn't have to push onto the list and all those things. We basically extracted one and said that this is storage. What would have happened if we had the exact same function, but we were using memory? So I'm going to call this actually storage. And then let's create an exact same function. And in this function, what we're going to say is that we want this to be memory. So I can show you the two different ways of how to do storage, or how to work with storage. So now we have the storage variable that we extract, and we can immediately update it. What happens if we wanted to use the memory, the temporary type of data location? Well, we could have put this to memory. And then what will happen is that we say that this NFT to be updated is now in memory, and it comes from this list, but this simply makes a copy of that item. So if we do this, if we say NFT to be updated name is equal to name, you can see that it doesn't change the blockchain, And from previously, you can see that the warning says that we can simply make this a view function because it's not updating the blockchain. What we'll need to do is still add this line where we have to select the NFT list and then go and find wherever this index is. So we still need to go NFT list, then go and find where the index is, like so. Then we have to go and maybe push this item to it or set this item equal to the new NFT to be updated, like this. If we do it this way, it accomplishes exactly the same as the way with the storage. But in this way, we basically make a copy of our NFT first, of our structure. We update the data, then we go and place back the data on that data index. We set it to be the updated data. If you can understand this concept that storage is basically wherever you see this, it basically touches the blockchain's data, the storage variables directly, and memory storage location only creates a temporary copy of it until this function ends. So you have to then reset it on the blockchain by explicitly telling it here that we are replacing an object in the blockchain. Lastly, we get something called call data. Call data is something you won't see very often, but for instance, if we had something extra to work with, such as an array of names or something, let's maybe create a new function over here, and let's say that this function, for the argument's sake, was add NFTs. Now, if we didn't have any way of explaining how to add NFTs, and we wanted to add bulk NFTs, you can specify it, and let's say we want to pass in NFTs array, and then especially with arrays, apparently you have to make it call data, okay, and then we're going to call this our NFTs, like so. Then what will happen is that we can maybe append this to the list, but maybe this is our base function and we directly want to just add these to our list. So we can maybe make the list and set it equal to our NFTs. This is just an example. But call data usually goes for arrays, what I have noticed so far. Anyway, with this knowledge, you'll be equipped to know exactly when to use storage or memory in front of a data type that's inside a function. I hope this is clear and that you guys understand memory, storage, and callback now. It's very simple, and those are the only storage data locations that you'll be using in Solidity. Finally, I get to explain to you guys what functions are and how they work. So go ahead and create a myfunctions.sol and give it the base definitions over here of a contract, a pragma line, and a license. You can then also go ahead and create these 4 variables. We've just created an integer, a string, a boolean, and an array type for me to show you how to work with functions and different parameters, as well as how to execute data and return data. What we want to do, and remember that these variables are seen as storage variables, they live on the blockchain. What we want to do sometimes is update the storage variables. We want to make a change, we want to return something to a user, or we want to act on data being given to the blockchain. How do we do that? We use things that's given to us to make it easier, like functions. Functions can contain any type of logic and can also call other functions inside of a contract. Let's create an example of that. To create a function, we need to create a function signature. Much like creating variables, we start off with a keyword. This time it's called function. You've seen me use it in the previous videos, so you might be used to this by now. A function can have a name, and we do need to give it a name. So let's give this function a name, and let's basically call it myfunc. Now, myfunc over here needs parameters sometimes, and parameters can go in between these brackets. What are parameters? Parameters are things that's given to a function on the call of the function. So for instance, if we wanted to call this function, we sometimes need to present it with some extra data for it to work with. Functions also don't need to have parameters, so I'm going to explain to you that as well. I'm going to say that this is going to be public, and then we need to open and close the curly braces. Like we've discussed before, public is the scope of who can call this function, so that's why this would be there. So that means that everyone outside of this contract will be able to see this function, and whatever is inside this function up until the last curly brace of this function will be executed. Now, functions can have if statements, loops, it can have data manipulation, it can basically do anything you want it. Functions also come in a wide variety of signatures. Like I've explained before, we can have pure functions, view functions, functions that return data, and we're going to explain them all right here, right now. Let's take an example of the very basic function that literally does nothing, but only return to us something that we've explicitly explained. So we are going to call this my pure function. So func is just a shorthand name for function. So let's call it my pure func. And basically I want this function to take in a parameter. Well, it doesn't even have to. By the definition of a pure function, it just doesn't need to depend on anything of the blockchain. So let's give it two parameters if we wanted to. So how you specify parameters, you give the data type. Then I usually add an underscore here to determine and to tell myself this has nothing to do with Solidity, but to tell myself that this is a parameter and that I'm going to be using it only in this function. So let's call it x. So we're going to pass in an x and we're going to pass in a y, like so. We can call it whatever we want to. But I'm just going to take these two arguments as an example. Now, let's go ahead and create a pure function. Like I said, a pure function cannot touch the blockchain at all. So let's say we wanted to work with the data x and y. Let's say that we actually want to take and see what is x, because we know it's an integer, plus y. We can do that, but we need to kind of return it or do something with the data, at least so that we can see that this function is a useful function. We don't want to create unuseful functions. At this point, this function would be seen as pure, and the warning will tell us that this should be pure because it's not doing anything to the blockchain. That's why sometimes after the public, you can specify the word pure, view, virtual, and override. There's a bunch of these how can I say, names that you give a function to tell the Solidity compiler what it's basically its purpose is. And this is pure because it's not changing any of the data over there. Now, to make this function useful, we can return something from a function. We can basically return this to the user because currently only this function will know about this, execute, and not do anything else. How do we return values in Solidity? You specify the returns, plural, statement, and then in brackets you tell it which data type you want to return. Now, because we are using UN256, we can work with UN256 return values, or we can cast it in some kind of other value. It doesn't matter. By the time of the execution of the function is done, and we then have by that time turned these into a string, for instance, we can return a string as well. But we're going to keep it simple, and we're going to return one value, that is UN256. You've seen me sometimes just put in a data type in here, but we can actually call this something, and we can call it maybe the result. When we do this, we're just basically giving a name to our return value. So this doesn't change anything, and as soon as we do a return, we can now see that, what does it say? Remove comment out the variable name or to silence the warning. Okay, because we need to comment out this because of a warning, but we need to return it. So let's go ahead down here and say this is going to return this answer, just to eliminate that warning, right? Because if there's no return of a uint, it's going to complain. Now this function will work regardless if you have this result or not. It's just a declarative name. So whether you have result in here or not, or any other, maybe X and Y, this is now XY, returning XY, whatever you want to call this return statement. But we are returning the sum of this, okay? So just so that you understand, pure functions defined like this with the pure keyword tells us that this doesn't touch any of this storage data, nor does it even return any storage data. It doesn't change anything. It's basically a function that doesn't even have to exist in the smart contract technically, because it doesn't use any of the data. Sometimes you use pure functions as utility functions. I'm going to duplicate this function, and then here we're going to look at what happens if we return some of this data here at the top for ourselves. All right, there we go. So I'm going to call this my, and you see that this compiler complains because we can't have the function with the same signature. If we had a different signature, it won't complain, because then this function signature is different. A function signature is recorded in the Solidity compiler and then creates an ABI, how functions looks that you call. So the names can be the same, but the signatures can't be the same as well. This is the function signature, and this has to basically be different to this if you want a function with the same name. But we are going to change the name just for clarity's sake. So we are going to call this my view function. My view function isn't even going to take any parameters. We don't want to give it parameters. We want it to return something. In this case, I'm going to take the alias away because I want to show you that you don't need that alias as well. We're also going to have this actually return a string. And remember what I said, when you are returning anything like strings, arrays, and structs, you need to specify what memory type we are going to be returning. So I'm just going to add the memory in there. So this is not the alias like that. You can still give it an alias and saying my string, right? You can still do that. But we just want to return a string. This function is now going to be changed to view. And why is that? Because we want to return my string, like so. Basically, this is now depending on data outside of this function, and that's why it's a view function. It's not altering that data. If it was altering that data, then we can't make it a view. So that's what I'm going to explain next. We're going to have this function, and basically this function is going to now explain to us. And I just always hate Solidity's compilers structuring of formatting. It's very difficult to format code in here and make it look nice. But anyway, if we wanted to use this function, but let's say my update function. So let's going to call it my update function. And now you can see everything is still fine, but we are not changing the string yet. So let's go and change the string. So we're going to say my string should now be equal to HashLips. Once we've done this, right, you can see that the compiler now recognizes that this is no longer a view function, and it also doesn't return anything because it doesn't return return this. We can go ahead and then after this go and say return my string, like so, but we also need to specify then what we're working with. So if this was my string is equal to this, and we return this, let me just see, default payable, Okay, so we need to, let me just see. We can't have this as a view, right? All right. So if we did this, then we're still returning the string after we changed it. But let's say we don't want to even change and return this function. We can also take away this return statement. But this updates the data that's sitting here on the storage variables. And if we do that, we can no longer have the view there, explaining that this is simply a view of the data function. This is now an update function, and whenever it's not a view, you will see when we do a compilation, if we actually compile this. So let's delete this previous one. Let's deploy this. You'll see that the button actually turns orange because it means that this is going to be a transaction. This is going to ask you to pay gas fees to actually perform this action in this function. All right. There's our peer function, so we can go ahead and just give it some integer values. So let's open this up. Let's give it a 3 and a 3. And we call it and we get 6. All right. And that's our peer function in action over there. Our myView function simply is just going to return the name. And then when we update the name, we've called it. It's going to call this. It's going to update it to HashLips. And when we view the function again over here, we get our new name back. That's just simply functions, the basic functions that you have, and kind of working with the view. Now, there is something extra that I want to explain, and that is the scope variable. There's an extra variable that you can add to functions, which is external. Now, you do know that we get private. Private meaning that only this smart contract will have access to this function, so we can call this function inside of itself. We can basically go and in this function, for example, go and call the view function and execute it actually like this. You execute a function by giving it its brackets, and if it needs any parameters, you put it in, but this basically calls this function. It won't be useful to us here at the moment, but maybe we can save the data that it's being returned. So for instance, if we wanted to save the data from that function above, we can do something like this. We can say string, maybe we want to specify it as memory, and I'm going to say this is my saved string. All right. If we do something like this, we basically taking the return function, we're taking the string that's being returned from this function because we are calling it, and we're saving it to a new string because it's returning as a type of string to memory. And then maybe we can return that string, right? Just as an example. So this is just a way for us to work with functions and see how it works. It's pretty cool. So anyway, that being said, after these functions are declared, like I said, there's another one. There's not only private, there's public, there's also external. External functions, and this is the last like scope type that you have to know about, but external functions can only be called outside of the contract. It can only be executed by a user executing a transaction. And this is sometimes very important for security reasons. If you don't want the contract to do certain things and only have certain functions being called externally. We'll see more about this in the future, but for now I'm going to stick with this and leave you with the public, private, external, and maybe I also just want to show you that we have the internal one as well, right? But anyway, I think the most important part of a function is the fact that you can return and you can see how a function works. Lastly, I'm just going to add a function down here, and we are going to call this function, we are going to call my returns function. And returns function, let's basically say we wanted to return this integer, so we're going to say we want to return a integer like so. We're not gonna have to give it the memory type, but what if we wanted to return multiple values? We can do that by specifying a comma, and then specifying what else we want to return. So we want to return a string. We're going to want to return this boolean, and we also going to want to return this array. Now, because the boolean of the string and the array is a type that needs to be allocated, we can specify that these both can be memory that it needs to return. And then once you're here in your return statement, all you need to do there is specify the order that you want to return your data in, which is basically going to be my uint there at the top. Let's go like that. My uint, my string. We also want to specify the my bool as well as the my array. All right. This function we will not have access to outside because it's internal. So let's go and make this public, or actually let's turn this one into external, and then this one we'll leave as public just for the example purposes. So you can see that I can call this outside of the function, outside of the smart contract, not the function, but the whole smart contract. If I click deploy now, I can see that I got my my build thing, and there it is here below. My returns function, if I click on it, here I get all the data that I said I wanted to be returned that's actually sitting on the blockchain. So that is very cool. And lastly, I just wanted to show a function that has no returns, because sometimes people mistake this and think they have to have returns. You don't have to have any return statements over there. You can just say this is now a no return function. And a no return function can be anything. It can update data, it can do certain things. Maybe in this case, no returns will just update our bool. So we'll say my bool is equal to false now. And maybe that's just how you want to use it. And because this is now altering the data, we cannot have this as view anymore. And we have to take the view off. I hope this gave you guys a broader understanding of functions and how we work with them, how it returns data, the different levels of access functions has, the fact that you can call functions inside functions. And because functions exist in this functions contract, if we inherit it from this smart contract like I've showed you before, but we'll get to inheritance, all these functions will be available, especially the ones that is not private, will be available to the contract that inherits from this smart contract as well. And then if this contract lives on the blockchain, everyone that sees the blockchain on Etherscan, on Polygon scan, can interact with these functions. I hope that is very clear, guys. But anyway, we're going to continue with our journey. Thank you so much for watching this video. I'll see you in the next one.